Hi, I'm Antonio Sala, and in this video we are going to continue with our case study of the control of the double integrator. In particular, we will discuss model-based design of a proportional derivative controller via a pole placement methodology. Let us first recall what we did in previous videos. Our double integrator plant modeled a half a kilogram mass to which I could apply an arbitrary force, capital F. We thought that friction was negligible or it was suitably compensated. If based on speed, I can compute an approximation of friction forces so that I can apply them in the opposite sense. So in that situation, my transfer function was 2 over s squared. Our problem setup was being able to move from a particular point 1 meter to the right. The difference between the actual position and the desired set point R reference is the closed loop error. And apart from set point tracking, we wished to somehow reject input disturbances, some other forces caused by wind or by, let's say, non-horizontal tilting of the platform in which my mass is moving. And well, we decided to apply a proportional derivative controller which had this expression here. And in previous videos, we thought that this proportional derivative controller had a mechanical analogy in the sense that a force proportional to a distance is a spring and a force proportional to a velocity is a damper. But of course, in most cases, controllers are implemented via some sensing and actuating technology and control software. So we have the flexibility to change the constant just by typing on a keyboard. But well, the mechanical analogy helps us understanding what we are doing. Good, so this is our system. This will be the block diagram abstraction of our control problem. Set point, loop error, control action, input disturbance du, my double integrator plant 2 over s squared, and my controller. We will use the pink expression because it will be convenient for our computations, but in my simulation application we have used the cyan parameterization, so we will need to interchange at will between one another. They are equivalent. In previous videos, we simulated the application and tuned it by trial and error, or well, let us remove saturation and measurement noise for the moment being. Proportional control could not stabilize. Derivative control did indeed stabilize and had damping. And well, we also proved that we were able to track with zero error set points and ramps with the controller we are discussing, but we were not able to track with zero error input disturbances that appeared at this moment in my simulation. But okay, this was trial and error tuning or analysis given the constant, computing the closed loop poles, whatever. In the problem statement for this video, we will carry out model-based control design in the sense that we will get some error bounds and damping and settling time specifications, requirements, and then we will need to compute the proportional and derivative constants. So let's state our desired behavior performance specifications for my closed loop. We have two kinds of specifications, what they are called static, which refer to what should happen when the transient ends, and we will request that position error when we have step change in set point tracking is 0, and also when we have a step in input disturbance du, this part of the diagram, we will request my position error to be lower than or equal to, in absolute value, let's say, because usually the sign of the error is not of importance in most control problems. We just want the error to be small. For instance, optimal control does some sort of least squares fit. Well, the thing is that we wish that the magnitude of the error will be lower than 0.2 meters per Newton of disturbances. I mean, what does this mean? Well, input disturbances cannot be directly measured. We don't have a sensor for them, otherwise we would carry out what is called feed-forward control, but in this case, with feedback only, we cannot measure them, and also we don't know which will be the amplitude. I mean, we can specify the user for some ranges of set points and the speed of variation of the set point and whatever, and prescribe that in my contract. But disturbances will be whatever they wish to be. Then my precision request will be in terms of gain, saying that, okay, for every Newton of disturbance du, my final displacement must be less than 20 centimeters. So if somebody pushes with 1 Newton, I will displace 20 centimeters. If somebody pushes with 2 Newtons, my wind to my drone or whatever, then I will displace 40 centimeters in steady state in this part of the simulation. This is my requirement. And in this case, for instance, how large was the disturbance amplitude? Well, it was 0.6, not because we did directly measure it, but we have an indirect measurement. If we have a controller in operation and my controller ended up making 0.6 newtons of force in order to stop the mass moving, then if the mass stopped moving, it means that the resulting force is 0. So if my controller does 0.6, it means that disturbance must have been 0.6 in the opposite sense. So we have an indirect way of measuring the performance based on feedback controller, which is in itself an interesting thing to think about. So, well, in this case, for instance, with this controller, 0.6 times 0.2 newtons meter, we will require 0.12 displacement, and in here, displacement is too big, so it's not valid. We need stronger controlling, in particular stronger proportional action. We'll see it in a minute. Well, these are our design specifications regarding steady state error, and then my dynamic specifications will be settling time in this unit set point step of 2 seconds, and also my damping coefficient. I don't wish a lot of oscillation. My damping coefficient must be larger than, let's say, 0.7. What do I mean with damping coefficients? Well, my system is second order and without integral action and noise filtering. Our closed loop will also be second order. We'll see that in a minute. So a pair of oscillating poles can be expressed with this expression in the characteristic equation. So omega n is the natural frequency and chi is the damping coefficient, which must be more than 0.7. Then this will be my dynamic requirement on the transient. So static specifications refer to what should be when transient finish, and dynamic specifications do refer to how the transient must be. A fast, well-damped transient. Good. So these are our specifications, and then how do we compute the controller gains? Well, in prior videos, we proved that the transfer functions from set point R, input disturbance du, and measurement noise were the ones at the top. And assuming that measurement noise is sufficiently small, we will concentrate on set point tracking and disturbance rejection du. So the loop error, once replaced my plant and controller and remove denominators, will have this expression with this characteristic equation to compute the poles. This is why methodology is called pole placement. I will work with the characteristic equation and design Kp and Kd so that its roots are in a particular desired location. And then regarding static specifications, well, we need to check that what we are being asked is feasible, and for instance, the steady state error with respect to set point changes in here is 0 for step changes, and also it is 0 for ramp changes because the error has a double derivator. So any constant or straight line, let's say, in the set point will be, once the exponentials have ended, this double derivative of a straight line will be 0. So we can guarantee perfect step set point tracking as required. And regarding the disturbance rejection performance, well, in this case, we also discussed it in more detail in previous videos. The thing is that if I replace by 0 the s variable, then this number is called the DC gain of this transfer function. It is 1 over kp. And then this is the constant that multiplies the input to give me the output when every transient has ended, if the transient is stable. So in this case, for instance, 1 over kp must be smaller than 0.2, because this is what we are saying here. Our loop error must be less than 0.2 times the input amplitude, so this is it. 1 over kp must be smaller than 0.2, and hence kp must be greater than or equal to 5, 1 over 0.2. Good. Then the static analysis means that, okay, this is satisfied with my PD regulator, and the disturbance rejection will be satisfied if kp is greater than 5. Good. Let us now discuss the settling time and damping coefficient, and in particular, if my closed loop is of second order, the roots of this thing, which is the characteristic equation, will give me the poles, and then the poles of this thing, if I have some oscillation using the second order formula, will have a real part of minus chi omega n plus minus square root of 1 minus chi squared times omega n times the imaginary unit. So this will be the real part, and this will be the imaginary part if we are assuming chi is less than 1. And as we are happy with chi equal to 0.7, we will indeed set chi to 0.7, because the more damping I wish, the stronger the damping in our mechanical analogy will need to be, the higher the derivative gain, and derivative gains have the problem of high frequency noise amplification. So usually in control design, one does not make the gains higher than the minimum required, because higher gains mean higher likelihood of saturation and higher noise amplification. So we will indeed decide a damping of exactly 0.7. Then, if this is the real part, if settling time is 2 seconds, as settling time is basically 3 over the absolute value of the real part of the poles, assuming of course that the real part is negative to be stable. Well, this is the settling time. In some books, instead of 3, you will have pi or 4. Well, okay, it's just 95%, 96%, 98% variations, but roughly it is this thing. So if this thing must be equal to 2, this means that the real part of the poles must be 3 over 2, 1.5. If settling time must be 2 or faster, this must be equal to or lower than 2, let's say. So the thing is that the real part of the pole must be at least 1.5. So we are almost there, in the sense that if this is 1.5 and we settle for chi equal 0.7, then 1.5, well, minus 1.5 must be equal to minus 0.7 omega n. Hence, omega n must be 1.5 over 0.7, 2.14, and then we can compute the imaginary part, of course, or well, we can just compute the polynomial coefficients. But the thing is that, well, this is the limit of real part, in the sense that real part was minus 1.5 or minus 2 or minus 3 or minus 7 to be this thing or faster. So instead of 1.5, we can put any larger number if we wish, so omega n must be greater than 2.14. So good. The thing is that the denominator of the transfer functions we are considering was this thing. So now we need to put everything in place and try to get the formula, to get the values of kd and kp. So if we copy this to our slide we are working now, then we have from settling time consideration that if this is omega n, then we need 2kp to be larger than omega n squared. So kp must be larger than 2.29. This is required from settling time considerations, but if we remember from position error consideration, we required kp greater than 5. So we will need to set to kp equal 5. Then if kp is 5, this will be 10. So we'll settle for omega n equal square root of 10. And then this thing must be 2 chi omega n. Then if chi is 0.7, then this thing must be 2 times 0.7 times square root of 10. And well, this thing will be kd. So kd will be 0.7 square root of 10 equal 2.21. And then we have finished our control design problem. We have kp and kd. So we can write our regulator as this, but okay, in the simulation we need to extract 5 as common factor. So this will be my kc parameter and this thing will be my td parameter, 0.44. So let us simulate it to see if we achieved what we were requested to achieve. I put this slider to 1 because we are doing derivative of the error, 5 as kp, slider top right, and then 0.44 slider top right. So here we have our desired behavior. Let us see. Zero state error in setpoint tracking, done. Then my simulated disturbance was 0.6, so 20% of that will be the allowed error in centimeter, so it's 0.12. Then if we zoom in, here we have that the steady state error is 0.12, done. And regarding settling time and damping, let me even change the time axis and zoom in. Then we see that we were requested 2 seconds and our settling time is just 1.1 or 1.2 seconds, so we are faster than requested because we needed a higher gain to reduce the error. And then, well, it is damped well enough, so oscillations just disappear. It goes above the set point, but it never goes down again. So, well, this is what we were asked for, and this is what we achieved. What's the problem? Well, that in real life we have saturation up, so things are very different, because without saturation my proportional gain of 5 means that when error is 1, my control will be 5 times larger than what I am allowed to, so that's a problem. And in fact the derivative action in this point, the derivative of the set point, is theoretically infinite. We filter it whatever, but we have the derivative kick. So the maximum amplitude of my control in theory is more than 20, but in reality it cannot be larger than 1. So that's why we see a very different behavior from theory and real time. My theoretical requirement had led to too high gains, and in fact, apart from saturation, we have also measurement noise. So if the measurement noise is not filtered, this is rubbish. So I need to filter in real life that measurement noise to say 4 radian seconds or something like that. And then I need to take into account that if my gains are high, then saturation will make my fully linear non-saturating simulations or theoretical computations very different to what I will find in practice. So one thing is passing my examinations, but in real life, we need to think in which are the sensible requirements that can indeed be achieved given my force limitations and my non-ideal sensors that have some noise that needs to be filtered. Then if I require slow enough specifications, then theory and practice will be similar. If I require specifications with too high gains, then theory and practice will be very different. So in fact, in here, my problem was the excessive gain needed to make this error small. So maybe a more practical solution would have been lower gain, more filtering, and solving this error here by integral action. But the design with integral action will be left for brevity for the next video. In here, if we summarized, in this video, we designed a controller based on some static requirements on the steady state error that required me a proportional gain of 5, and then also from some settling time and damping, we deduced a lower bound for the natural frequency that was a different lower bound for the proportional gain. That, okay, the error one was the winner, and then we, with this 0.7 damping coefficient, we were able to construct the desired denominator of the transfer functions and compute my proportional derivative gains, which transform to the parameterization in my particular simulation, gave me a very nice simulation in accordance to what was requested. But the gains were a bit on the high side, so I had saturation problems, and of course all derivative controllers have noise amplification problems. They need some filtering. So well, the theoretical design we did was not that good on the saturation and measurement noise situations, but well, in a first course on automatic control, if the saturation-free and noise-free simulation is good, then you get a high mark in your examination. And that was the goal of this video. So we finish here. Thanks for watching.